Alright, so let's start. So looks like people have not joined today, so it's okay. I will anyway be uploading this this session on the YouTube channel. So those people who have not joined today and want to see the video, they can simply refer to the video in my YouTube channel. So I'll be starting with the this week's content now. Yes, welcome back to the course. This course is Basic Electrical Circuits, and it is taken by the instructor Dr. Ankush Sharma. He is a professor in the Department of Electrical Engineering at IIT Kanpur. I am the tutor for this course. My name is Mayank Anupam. I am a PhD student and a PMRF scholar, and I am also from the Department of Electrical Engineering at IIT Kanpur. Alright, so moving ahead. In this week, that is week 9, not this week but the last week. Okay, so the last week you learned about sinusoidal steady state circuits, right? So you learned about ways to analyze sinusoidal steady state, the circuits which are excited by a sinusoidal source, and you analyzed its steady state response, right? So you found out transfer function and things like that. You found out what is you solved some circuits, some circuit equations. You solved some basic circuits, right? So let's move forward and see what we learned. So this is a quick summary of the week. So whatever you learned in this week. So this week was just a extension of the whatever you have learned already for DC circuits to the case where the circuit is excited by an AC source, a pure sinusoidal source. Okay, so here also all the you already know that you can represent a circuit excited by a pure sinusoidal source using phasors, right? And when you represent everything in terms of phasors, the circuit is very easy to handle because you get away with you completely remove the time dependence, right? So you do not care about the time dependence that you add at the last. All the analysis which you do will be same as that you have learned for the DC circuits, and you can simply use them if you introduce the concept of phasors, right? So in DC circuits you learned about nodal and mesh analysis to solve circuits, right? This is a very general form of analysis to solve any circuits. So here also we will be using the same thing, nodal and mesh analysis. You learned about that. After that you also learned about superposition theorem, source transformation, right? So you learned, you actually saw how to use superposition theorem, source transformation for the case of sinusoidally excited circuits. Fine. You also saw Thevenin's theorem, Norton's theorem, maximum power transfer theorem, right? So Thevenin's theorem and Norton's theorem are almost the same. So not almost, but exactly the same. But maximum power transfer theorem is slightly different in this case, right? So in the case of remember that in the case of DC circuits which were excited using a DC voltage source or current source, there the maximum power transfer, there actually you didn't have any capacitor or inductor, right? Or even if you had, it didn't matter, because when you talk about DC circuits or when you talk about the steady state, they are as good as saying that they are not present, because capacitor will simply become open and inductor will simply become short, right? So in that case you learned that for maximum power transfer to a given load, not to a given load but actually the maximum power that can be transferred to a load, that condition occurs when the load is matched with the source resistance, right? So let me write it here. Sorry, one second. sorry, 1 second. Yeah, I'm sorry for that. So you learnt about, right, so if this is a voltage source here, so this is plus, this is minus, and you learned that if this is a RS, and suppose here you are connecting an RL, so maximum power transfer, that is P max, occurs when P max occurs when RL is equal to RS, right? That was the case for DC. This was the case for DC circuits. Now for AC circuit, or rather for circuits which are excited by sinusoidal voltage source or current source, this condition is slightly different. Where in general you can have a complex impedance, right? So let's say this is a voltage source here, Vs, and you have a complex impedance Zs, source impedance, and you can in general have a complex impedance here also. Let's say this is ZL. Now the maximum power that can be transferred to this ZL load is, occurs when, in this case P max occurs when your ZL is equal to Zs conjugate. So basically the reactive part of this, the complex part of this impedance ZL should be negative of the complex part of this impedance Zs, and the real part should be same. Okay, in that particular scenario, when this condition is met, in that case you can say that the maximum power is being transferred to the load ZL. So this is a slightly different, this is what is different from the case of DC circuits. After that you also learned about magnetically coupled circuits, right? So you learned about inductors. No, you know already about inductors, but you also learned about mutual inductors, wherein you have two different coils placed side by side, or in some fashion, and the flux from one flux emanating from the one coil links to the other coil and creates a current in the, or creates an EMF in the other coil. This is purely by the effect of magnetic fields. Okay, so that is why it is called magnetically coupled circuits. You have not actually connected them, but they are being coupled by the magnetic field. Okay, that is why magnetic coupled circuits. They are mutual inductors. Now you also learned about ideal transformers, right? Ideal transformer nothing but they are simple mutual inductor. Okay, they are inductors, mutual inductors, wherein the coupling coefficient is equal to 1 here. That is all the flux that is coming from the one coil is completely linking with the second coil. So magnetic field for both the magnetic flux for both the coils will be same. Fine, move forward. So this was what you learned in this this week, right? This was a quick summary. Now let us go to the fun part, that is solving questions. Okay, so fine. So let's solve this question first. The first question is, so I'll be solving this question. You have to find what? You have to find the voltage at node 2 in this case, this particular node, right? You have to find the voltage at node 2 of the for the circuit given. I have already given the answer here. Now let us see whether this answer matches or not. This is the circuit. So let's solve this question. Enlarge it slightly so that it's easier to handle. So this is question 1. What do we need to do? We have to find V of 2. Let's say this is voltage at second, so I am presenting it as V of 2, V2. Fine. So let's quickly understand what is this circuit. You see, there is a current source here, which is a sinusoidal current source. It is represented in terms of a phasor. Okay, the magnitude of the current source is 20 ampere, and the phase lead is actually equal to 30 degrees, right? So the phase lead is 30 degree. This is a sinusoidal current source here. Now you can clearly see that this impedance here and this impedance here, they are in parallel, right? Also the same thing is can be said about this impedance here and this impedance here. So these two are in parallel, these two are in parallel. Okay, so let's call the parallel combination of, so let minus J2 parallel, sorry, minus J2 parallel 10 equal to Z1. Sorry, someone is trying to join. Yeah, so this is, let's call this as Z1. Okay, now again let's call J2 parallel minus J5, which is this part here, let's call it as Z2. Okay, and there is a third one here, J4, which is not parallel to anyone, let's call it as Z3. So it is easier to handle when you write it in terms of simple names. Okay, let's J4 be Z3 and let 20 angle 30 degree ampere be I. Okay, so I'm just trying to represent all of this using an equivalent circuit. Let's see how does it look. So what will be the equivalent circuit for this case? The equivalent circuit will become, let's first write this current source I1, okay. Now one node of I is this first node, right? This is the first node, this is the second node. So this current source has two nodes, right? This is the first node, this is the second node, this is the first node, 1, this is 2. So similarly I have written here 1 and 2, right? Now the second node is connected to what? Second node is connected to the impedance. This is what? This is Z2, right? This is Z2. This parallel, this are, it is Z2, and then it is grounded here. Fine. Similarly, node 1 is also connected like this, and this is Z1, right? So this parallel, this is Z1. Okay. So node 1 to ground here. Fine. Now you see Z3 here. Z3 is this this one. This we have represented as Z3. Okay. So this is Z3. This is between connected between node 2 and 1. So we will connect between node 2 and 1. Z3. Okay, someone wants to join. Let's. Okay. So this is Z3. Fine. So now we have to find out what? We have to find out the node voltage V2. V2. This is V2. Let's say this is V1. With respect to this reference, right? So reference is already provided in the question. This is ground here. So this is ground here. With respect to this ground, reference is treated as 0 volt, right? This is 0 volt. With respect to this 0 volt, what is the node voltage V2? So you can see that since both these nodes are at same potential, that is at reference 0 volt, I can simply connect them up, right? I do not need to do this separate ground for them. I can simply connect them and this. So I can simply connect them like this and put a reference here, right? This is 0. Okay. Now you have to find out this voltage. By the way, this is current I. Okay. You have to find out this voltage V2. So there are two ways to solve this. One is brute force method, when you write KCL and KVL for each and every node, you find it out. So that will be messy. Okay, so that will become extremely messy. In fact, I have solved this question earlier. So I'll show you how messy this becomes. So I solved this using the brute force method. I wrote KCLs for node V2 and V1, and this is what I was getting. This was extremely complicated till here. After that, the algebra would have become extremely complicated here. So an alternate or easier method in this case would be what? Would be to observe something, right? So Remember age old source transformation. So in this case you see this current source is in parallel to this this impedance Z3. So you can clearly see that you can clearly use source transformation here, right? Source transformation can be applied here, and the equivalent after that would become what? After source transformation, what will be the equivalent circuit? The equivalent circuit will be like this. So you have a voltage source in this case. This is the voltage source. Then there is Z3, no, not Z3, but Z3. Okay. And then you have this Z2. You have this Z1 here. And you have this ground here. Fine. So this is the equivalent circuit. And okay. Basically we have applied source transformation between these two nodes. Okay, these two nodes. So these two nodes are here. And what is this voltage source value? This is I times Z3. Okay, fine. So now it is very clear what is this circuit, right? You can clearly see that all these three impedances, they are in series, isn't it? You see all of them are connected from placed terminal by terminal. So terminal 1 is connected to, second terminal of this is connected to first terminal of this, and then the second terminal of this is connected to the first terminal of this. So they are placed side by side here, isn't it? So they are clearly in series. So what will be the and what do we need to find out, by the way? We need to find out this voltage V2, isn't it? This is V2, this is V1. So what will be the voltage V2 in this case with respect to ground? So first we need to find out what is this current. Okay, what is this current? So what is I? I is equal to this voltage source Vs. So Vs divided by Z1 plus Z2 plus Z3. And what is Vs? Vs is equal to I times Z3, right? I times Z3 divided by Z1 plus Z2 plus Z3. So this is the current that is flowing in this direction that I have shown here. Now this current, when flows in this direction, this current creates a voltage what? V2 is equal to Z2 times I, right, with respect to ground. You say this is equal to 0 volt. If you apply, so this is equal to 0 volt, right? If you apply if you write simple equation here, it will become V2 minus 0 divided by Z2 is equal to I, right? I have applied KCL here. KCL at this this node, by the way. So current coming here is I, and the current flowing out of here is V2 minus 0 divided by Z2. So it shows that V2 is equal to I times Z2, right? So what is the voltage V2, the node voltage that we are interested in? V2 is equal to I times Z3 divided by Z1 plus Z2 plus Z3 multiplied by Z2. Fine, this is Z2, so multiplied by Z2. So this becomes equal to what? I times Z2 Z3 divided by Z1 plus Z2 plus Z3. Such a simple this thing equation here. Now you can put the values of Z2, Z3 and all to, here, and you can get the answer. So the answer is here. This is the answer. You will have to do a slightly. You have to be slightly careful while doing the calculation. So it involves. Yeah. So it involves, by the way, it involves complex algebra. So you have to be careful about it. So you will get this answer. Okay. Fine. Any questions in this question? I mean, any doubts in this question? Fine. So let's move forward. Now this is the second question. Let's solve this also. What do we need to find out in this case? We have to find out this voltage V0. Okay, this voltage V0 here for the circuit. this is the wrong answer. Yeah, so we have to find out this voltage V0. Voltage V0 is this one, right? For the circuit given. Let's do that. So this is question number 2. Find V0. Okay, for the adjacent circuit. Okay, let's do this. So here also, we have to find V0 in this case, right? So other than introducing this complex impedances, it's simple. It is very simple, right? It's a very simple circuit. It's a voltage controlled voltage source here, and there's a current source here. There are impedances here and there. So it's a simple circuit which can be solved using any of the techniques that you know, like nodal analysis, mesh analysis. Okay, so I will be using nodal analysis because that is I feel comfortable with that. So let's go. So this current here, this voltage here, let's say this is so this is given, right? It's V0. This will be V0, and we know that the voltage here at this node, by means of this voltage controlled voltage source, so it should be in this direction, minus to plus. It should be 3V0, right? So fine. Now we know the two voltages here. Okay. Now let's find out this. Let's solve the circuit. Okay. So current coming here will be divided between this and this, right? So current that is coming here, let's say this is I, this is I, let's call this is I1 and this is I2. Okay, so I is equal to I1 plus I2. Okay, so this implies, what is I? Let's call this as I only for time being. What is I1? I1 is this current, right? It's equal to V0 divided by 2. So Ohm's law here, right? V0 divided by 2 is the current here, plus I2 is this one. So V0 minus this voltage here. So V0 minus, and what is the voltage here? It's minus 3V0, right? So this is plus. By the way, this is a reference here. This is 0 volt. This was 0 volt here, and this node here is 3V0 less than this 0 voltage. This is equal to minus 3V0 divided by which impedance? J4, right? J4. So this is the two currents. These are two currents. So only so now you can see that this equation is all enough for our solution. So I is equal to V0 is taken as common, and 1 by 2 plus this is V0 plus 3V0, 4V0, and V0 is common outside. This is 4 by 4 J. This becomes V0 times 1 by 2 plus, or rather, let's solve this here. It becomes 1 by 2 minus J, correct? Fine. So what will be the final value? So this is I is equal to V0 times 1 minus 2J by 2. This becomes, this gives V0 is equal to 2I divided by 1 minus 2J. Okay, so you have found out what is V0 here. So let's write V0 here is equal to 2 times, and what is I? I is 4 angle minus 30. So this is equal to 4 angle minus 30 degree divided by 1 minus 2J. This becomes 8 angle minus 30 degree divided by 1 minus 2J. So I will not solve the complete this thing. I will only check for the magnitude part of it, right? I will only solve the magnitude part of it and use find out the angle of this. So V0 will be V0 will be a phasor, right? It will have a magnitude as well as a phase, right? Just like current was what, 4 angle minus 30 degree. So 4 was the magnitude of that current, and minus 30 degree was what? It was the angle of that phase of that particular current. So similarly, this V0 will have a magnitude part as well as phase part. So I will only be calculating the magnitude here. Fine. So magnitude of V0 is equal to magnitude of 8 angle minus 30 degree and magnitude of 1 minus 2j. This becomes magnitude of 8 angle minus 30 degree is simply 8 divided by this magnitude is what? Root 5, correct? So 1 plus 4 under root. So this is 8 by root 5. So this is the magnitude, and you can find out the angle yourself, right? So this was the solution of this question. So it's very easy. It's simple, very simple, and it was, you have already done this for the DC circuits, right? So it's just that you have to be a bit more careful here while solving these circuits, because it has complex numbers in it, right? You have to be careful while handling them, otherwise you will make silly mistakes. Fine, moving ahead. So the third question. Okay, let's solve the circuit. Yeah, so let's solve the third question here. This is third question. We have to find out this current Ix here. Okay, so this is okay. So you see that there is a voltage source here, there is a current source here, right? So you can use it. You can use three methods, okay, for this for solving this. You can either use your brute force mesh analysis or node analysis in this case, or you can do superposition theorem. So what was superposition theorem? So this circuit is linear, okay. This circuit is this circuit is a linear circuit, so you can use superposition here. What did superposition say? Superposition said that the net total. So in this case, the total current here will be equal to what? The current due to this voltage source only, when basically this current is switched off, plus the current due to this current source only when this voltage source is simply shorted here. Fine. So that was superposition. So but that will also be slightly messy in this case, because we'll have to solve this circuit, the same circuit, 2 times. Okay, so that is simply messy. Another method here can also can again be source transformation. Okay, so you can simplify the circuit very quickly when you use source transformation. So what do I mean by that? You see here, this circuit here, you see this voltage source. Why do you move this? Let's first write the question, by the way. Find Ix in the adjacent circuit. Okay, so how do you use source transformation? You see this voltage source here. This voltage source is in series with this impedance here, 2 plus 4j, right? So this can be transformed into an equivalent. So what will be the equivalent after source transformation? Source transformation. So this will become a current source like this, and a parallel impedance here. Current source value will be what? 60 angle 0 degree divided by 2 plus j times 4, and this impedance will be 2 plus j4. Fine. And then there will be this impedance 6 ohms here parallel to this. Then there will be this capacitor here, its value is minus j2 or minus 2j rather, minus 2j here, then there is this 4 ohm this thing, and then again there is a 3 ohm minus j3, okay, minus j3, this is 4 ohm, and then there is a current source. Fine. Okay, cool. So you have to find out this current. Now again you can see that I will also fine. You can again see that in this case this this impedance here and this impedance here, they are in parallel, right? So you can use parallel equivalent circuit equation to find out the equivalent of this. So let's call that as Z1. Okay, so let's call this guy here as some Z1. Okay, so what will be the, after that parallel thingy, what will it become? Equivalent. So it will become, this is the current source here, then there is a Z1 impedance here, then there is this minus j2, then there is this 4 ohm, then there is this minus j3, and this is 4 ohms. This is current Ix, this is the current source. Fine. Fine. So by the way, let's call, this is extremely complicated to write, so let's call this as I, simple I, or let's say this is I1. Okay, this is I1 here. Okay, now you see again this I1 and this impedance here, yeah, again this I1 and this impedance here, which is Z1, right? So this we wrote as Z1. This I1 and Z1, they are in parallel, and hence they can be transformed. Here also we can use source transformation, right? So use source transformation again. Source transformation again will give what? So we will get a voltage source here. Its value will be what? I1 times Z1. We will get a Z1 impedance here. We will get this minus j2 in series with this, then we will get a 4 ohm here and a minus 3j. Fine, minus 3j, this is 4, and this was the current Ix. Then this is the current source here. Let's call this current source as I2. Okay, so we write it I2. Fine. Now you see that this and this, they are in series, right? So they can simply be added here. Correct? So let's add it and write out. So after addition, this series impedance, so let's call this as Z2 after addition. So another equivalent circuit will become what? Equivalent will be like this. This is I1 times Z1 multiplied by, this is Z2, so this is Z2 here, and then there is this 4 ohm here, then there is this minus 3j, 4 ohm, this is minus 3j, there is this current source I2. Fine, and you are interested in this current Ix. Again, I will do source transformation here. You can see that this is a voltage source, by the way. This was a voltage source. I1 times Z1, this is a voltage source. This voltage source is in series with this current, this impedance here. So I will simply use source transformation again. Source transformation. So this will give what? The current source. I will get a current source again, whose value will be I1 times Z1 divided by Z2. Fine, and I will get a impedance Z2 here. I will get another impedance, which is, So let's simply write 4 ohm minus 3j. These are in series, right? And since I am only concerned with the current here, so I'll write it as 4 minus 3j. Fine. This is the current Ix. Then there is another current source here, which is I2. And now you can clearly see that this I2 and I1, this I2 here and this current source here, whose value is I1 times Z1 divided by Z2, these are in parallel. And when two currents are in parallel, what do? They simply add up, right? So I can represent it as, so again equivalent here. So this is the current source. I have this current source here, a single current source. Then there is impedance Z2. Then there is impedance, this is 4 minus 3j. This is the current that I am interested in. This current will be what? I2 plus I1 times Z1 divided by Z2. Fine. Now you can see this circuit is so simplified, right? The Ix will be in this case what? It's a simple current division between a parallel circuit, between two parallel connected impedances. So you already remember the formula, right? So the current Ix in this case will be equal to what? Total current, that is equal to I2 plus I1 times Z1 divided by Z2. Total current multiplied by inverse, the opposite impedance. The current which you want to find out is in this impedance, so you'll be multiplying it with this impedance here, right? This is Z2 here divided by Z2 plus 4 minus 3j. So this is the total current. Fine. So you can solve the circuit, you can put the numbers here of Z1, Z2 and Z3. So Z1, Z2 and all the numbers you can put here, and you can calculate the value here. Fine. The answer is this. So try it on your own. Fine. So going forward, this is a very interesting question. So we want to find out the value of X that will give maximum power transfer to the 20 ohm load. This is the value of, so this is X here, right? Minus Jx, this is a capacitor. So you want to find the value of X that will give maximum power transfer to this particular load, right? So let's solve this. Fine. So this is question number 4. Okay. So point X which will result in maximum power transfer to 20 ohms load. Right? Okay, so this is a question of maximum power transfer. So how do you solve the maximum power transfer questions? If you are given a network, right? So there is a network, and that network is terminated by some load. This in this case the load is 20 ohms. The network is this whole thing here, and you have to find out what is the how you can change the network so that a maximum power can be transferred into a given load. So here the load is fixed, right? So if you want to find out maximum power transfer, condition for maximum power transfer, what do? You first find out Thevenin resistance when you look into this network from this port, right? So you have to find out the Thevenin resistance. So how do you find Thevenin resistance? You first write it here. So step one is find Thevenin resistance RTH. Let's call it A B cross AB. looking into the network. Yeah, so how do you find out the Thevenin resistance for a given network? You first desensitize all the independent sources in the network, right? By desensitizing, what do I mean? I mean that if there is a voltage source, you have to short it. Independent voltage source you have to short, and independent current sources you have to open, right? So there is the voltage source, independent voltage source here. You have to short it, right? So let's short it and write out the and then find out what is the equivalent. So listen to this problem here. The network will become like this. Shorted the voltage source. Then there is 8 ohms. This is 8 ohms. There is minus jx. Minus jx. Then there is this inductor here. Sorry. And then this inductor's value is 12. This is the dot placement here. And then there is another inductor here. What is placed here? This value is J15. And you have nothing here, right? I guess nothing here. Yeah, fine. So these are the two terminals. So across these two terminals, you want to find out the Thevenin resistance. You have already shorted the voltage source. Now what do you have to do to find the Thevenin resistance? You have to connect it to a voltage source of, let's say, Vs is equal to 1 angle 0 degree, and you have to find out what is the current here, Is. Fine. So Vs by Is will be your Z Thevenin. Okay. So let's do that. Oh, okay. By the way, this is this mutual inductance value is 10J. Fine. Okay, so it is 10J. All these things are in ohms. Okay. Fine. So let's do it. So if this is Is here, let's call the current in this direction as some I2. Okay. So now let us write out the equations. First, for this particular, let's write out KVL in this loop. Okay. KVL in this loop. So the KVL in this loop will be what? Vs minus J15 times Is, again then minus, this is mutual inductance, right? 10J times I2. So this is done because you see the dot convention here is in agreement with the current directions that we have chosen here. Current are entering these two dots here, and the voltages are like this. So that is why I have written it like this. So the current are actually entering in both the dots. So the voltages will be in this manner only. Okay, this is equal to 0. This is our first equation. And the second equation here will be what? For this loop KVL, right? So in this case it will become minus 8 into I2 plus minus of minus jx times I2, again minus of j12 times I2, then minus of 10j times I1 is equal to 0, Is equal to 0. This is the second equation. Now when you solve both of these equations, you will get what? You will get Z Thevenin equal to, so I'll simply write out the equation answer, right? Let's not get involved with the, this is slightly complicated. So when you do this, you will get this answer here. The Thevenin resistance Z Thevenin is this value. Okay, so let's So this is Z Thevenin, okay, and this is Z Thevenin. This is what you get, and you remember that this Z Thevenin here, this will be a complex value. It will come out to be a complex value here, right? And you remember that in the case of when the load was real and the Thevenin resistance was complex, the maximum power transfer condition was what? The load resistance has to be equal to the magnitude of the Thevenin resistance, Thevenin impedance, right? So here the Thevenin impedance magnitude, Thevenin impedance is this. So the magnitude of Thevenin impedance, which is this guy here, should be equal to 20, and this will give you the value of X as equal to, it will be basically a quadratic equation. You will get two values here, so both of them are both of them are valid. Okay, so here I've just given one answer, but there can be two answers and both of them will be valid here. Fine. Okay, so let's move ahead to the last question of this discussion. Yeah, so in this case, what is this? The primary of an ideal transformer with turns ratio of 5 is connected to a voltage. This is very wrong. This. The primary of an ideal transformer with turns ratio of 5 is connected to a voltage source with Thevenin parameters. This and basically VTH is 10 cos something, RTH is 100 ohm. Determine the average power delivered to a 200 ohm load connected across the secondary winding. Okay, so let's simply take a screenshot of this guy. This is question number 5. Okay, so you see, we have an ideal transformer. Okay, so we have an ideal transformer here, and this is okay. We have an ideal transformer here. To 5. The turns ratio is given as 5, right? This is the ideal transformer. Okay, now you see it is written that it is connected to an ideal to a voltage source whose Thevenin parameters are VTH is equal to 10 something and RTH is now. So this is connected to a voltage source. This is the voltage source here, whose voltage is something. This is its RTH and this is its VTH. Okay, and the secondary of this particular this transformer is connected to what? Is connected to a 200 ohms load. Fine. Okay, this is gone. Fine. So now we are interested to find the power delivered to this guy, 200 ohms resistor, right? So VTH is 10 cos 2000 T. So VTH is what? 10 cos of 2000 T. So what is this? How do you represent it in terms of phases? So there it will become 10, and cos of 2000 T will be simply 0 degree, because this is 2000 T plus 0 degree. In phases we do not represent this part. We only represent this this angle, this phase, right? So this is the phasor representation of this VTH. Okay, so now we can solve this simply. It is very easy, right? So you already learnt about what happens when we connect a load here, 200 ohms, to the secondary of the ideal transformer. It simply transforms this load to this particular node here, right? And what was the transformation? It was like this. So ZL gets transformed to ZL upon N square, right? So here it will be what? ZL is 200 ohms divided by N square. N square is 25. rather 5 square. What will it become? So it will become what? 200 by 25, it's 8. Okay, but this is 8 here, so the equivalent will be like this. Only the primary side will be looking like this. This is VTH, and there is RTH, which is equal to 100 ohms. Then there is this ZL, which is transformed here to the primary side. It is equal to 8 here. So you can find out the current here, right? The I1 current. I1 current is equal to what? VTH divided by RTH plus 8, which is equal to what? So VTH is 10 angle 0. Angle 0 is simply, we do not write it. So this is 10 divided by 108. This is I1, right? And what are we interested to find out? We are interested to find out this power delivered to the 200 ohms. So first we need to find, so we are already find out I1. So now we need to find out I2. Okay, and we know that for an ideal transformer, the relation between I1 and I2 is inverse of basically I1 by I2 is equal to 1 by n, correct? Inverse of the turns ratio. So from this I2 will be what? I1 times n, correct? No, sorry, I made a mistake here. It should be, turns ratio is 1:5, right? So it will be inverse, so it is n. So I2 in this case will become I1 by n. I1 by n. Okay, so in this case it becomes 10 divided by 108 into 5, 2 by 102 by 108, or 1 by 54, right? This is I2. So power dissipated in 200 ohms is equal to what? I square RL divided by 2. This I2 here is a phasor quantity. Okay, this is angle 0 degree phasor. So, and by the way, this 54, 1 by 54 is the magnitude. It's not the RMS value. So that is why we have to multiply this 1 by 2 factor here. So this becomes what? 1 by 2 times 200 times 1 by 54 square. So this is the answer. This much of watts. Fine. So fine. So that's it for today. So I have explained I have solved 5 sample questions here. So if you have any doubt, you can ask me in the next session, and you can go through all this solution basically you can go through my the video that I will be uploading shortly. You can go through that, the people who have missed the class, and you can ask me anytime later. Fine. So I guess that will be the end of the session. Fine. So thank you. So I'll be seeing you in the next session. Thank you.